As I said, we're working with rates of chemical reaction and chemical equilibrium. And first of all, when we look at rates of chemical reactions, we're first going to look at all the factors that influences chemical reactions. Secondly, we're going to look at types of questions that were asked in the last few years in exams. And we're also going to look at knowledge that you need to be acquainted with before you can effectively answer these questions. We're also going to look at methods to collect data in practical investigations, because many of the questions that we do get have practical investigations. We're also going to look at the two types of graphs that is important when we deal with rates of chemical reactions. The first one that you've done mostly in grade 11 is chemical potential energy curve, and then the second one is the Maxwell-Botzmann curve. I see we've got quite a few schools online, and I just want to welcome all of you. I am Mr. Weingart, I neglected to say, and I teach at Malibu High School. So without further ado, let's start. The factors that influence the rates of reactions are as follows. Firstly, the concentration of the reactants. I'm not going to elaborate a lot on these individual points, because what we have found is that learners do not have a problem comprehending them. We are much rather going to look at the more practical applications. Secondly, we have temperature, where we know that the higher the temperature, the faster a reaction will take place. Thirdly, it is reaction surface of solid reactants, and there we're talking about how fine or how rough it is. And I think there I'm just going to take a short break and go to the paper and explain to you what we mean when we talk about a powder or a granule and how it actually affects the reaction surface. If this should be a solid chemical compound, just one crystal from it, and I'm drawing it a bit big, and let's say it's a rectangular prism, what we find is that the surface where reaction can take place is in fact, I'm going to take another color, we find that we have two of these sides. We would have two of the top, which would be top and the bottom, and we would have the front and the back. So all in all, we would have 6 surfaces where the second reactant can come and make contact with this one molecule or this one piece of my first reactant. If I should now go and I break this into 2 pieces, so I break it into half, I will find that now I end up with 2 blocks like that. And what is added now to all the surfaces that I have above is I've added this inside surface and that inside surface, effectively giving me 8 total surfaces to react. And if we go on in that way, if you now should split this one and that one in half, we will increase the surfaces to 10, to 12, and so forth. In other words, what we find is that just a big piece would have a smaller reaction surface than a granule, which would be smaller. And that would have a smaller reaction surface than the powder. Because obviously, if I have ground this piece down to a fine powder, if I go according to the reasoning we have with going from a piece to a granule, then I see that I have actually increased the reactant surface of this reactant to a very great surface area. So that is why a powder has a greater reaction surface than a granule would have, and a granule would have a greater reaction surface than a lump or a big piece of the same material will be. And many times learners tend to think that if it looks big, the surface must be big. But it's actually the other way around. The finer the particle, the bigger the surface area, and the bigger the particle or the lump, the smaller the surface area that is available to react. So we can go back to our slides now. The fourth one is pressure, and obviously pressure is only applicable when our reactants is in a gas phase. The next one will be the nature of the reactants. And there we can make the example of an organic acid, it's like acetic acid or ethanoic acid, which is, as we know, a weak acid, versus sulfuric or hydrochloric acid, which are strong acids. And therefore, the nature of the reactants also play a role. Finally, a reaction can be speeded up, or the rate can be increased by the use of a suitable catalyst. And there we say suitable catalyst because it is important that we actually choose the catalyst carefully. And we also get the opposite of a catalyst is an inhibitor. So sometimes we can add something to a reaction to actually deliberately make it slower. But so in terms of reaction rate, we have concentration of reactants, temperature, reaction surface of the solids, pressure when the reactants are in gas form, the nature of the reactants, and the addition of a suitable catalyst. If we go further, I just want to go through a few questions that has been asked over the last few years. The first one is the preparatory paper of 2008. And what I want to point out here to you is, first of all, this is the Maxwell-Botzmann curve that we're going to do in more detail. And you'll see immediately it starts with a learner investigates. And then we're talking about a reaction between zinc and hydrochloric acid. So your knowledge of the reactions of acids and metals are quite important. In question 8.1.2, we look at collision theory. So the knowledge of collision theory and what the implications are on the reaction is very important. And if we look at 8.1.1, they talk about a condition that has been changed. So it's important to know all the theory and all the basics of the scientific process. In the same question, in the same year, we deal here with the chemical potential energy versus reaction coordinate graph. So graph work is extremely important when it comes to reaction rates. Then in November of 2008, just to repeat again, what's important would be collision theory, the words you see in 8.1. We talk about two conditions, once again referring to the different variables that we can have. Again, collision theory. Then we look at the notation in 8.2, where you can see how a chemical reaction is written properly with the phases. And the delta H, which is our heat of reaction, is given. Activation energy is 132 kilojoules. And once again, you have to be able to draw a graph and not only to interpret a graph. In February of 2009, once again, there is an investigation into the working of antacids. And it says a group of learners in 8.2 wants to investigate. 8.2.1, they ask for an investigative question. 8.2.2, an hypothesis for this investigation. So once again, the scientific process is extremely important, and that is why we do it with you from grade 8 onwards. And here we see in November of 2010, learners use sodium thiosulfate to investigate the relationship. And the reason why I picked this one is because many learners has not been exposed to doing this experiment, and therefore when they refer to sodium thiosulfate, it looks a bit strange, but the principles remain the same. I've also chosen this specific reaction to look at the different phases of the reactants and the products. And there you can see sodium thiosulfate, AQ for aqueous or watery solution. Sulfur is a solid. Water is a liquid, L. And so in that case we cover, and sulfur dioxide is a gas. So we cover all the different phases or forms in which reactants and solids can be, and therefore this is a heterogeneous chemical reaction because there are more than one phase present amongst the reactants and also the products. So the next thing we're going to look at specifically is methods that you need to collect information or data when doing an investigation. And this one I'm going to stand still. This is the reaction of sodium thiosulfate, where if we go back for a minute, you'll see sodium thiosulfate, we add hydrochloric acid to it. And what happens is that before the time, we make an X across under the solution, and it's clearly visible from the top. And when we add the hydrochloric acid to the solution, a cloudy sulfur precipitate is formed that covers that X. And therefore it's important that you familiarize yourself with all the reactions that can be used to measure reaction rate. So in this case we use a stopwatch to see how quickly the cross will be covered by the sulfur. Next one, this is a reaction of a metal with a dilute acid. It looks like magnesium ribbon. And the reaction vessel, the beaker, is placed on a scale, and then as we form a gas product, which is hydrogen in this case, we find that the mass of the beaker will decrease with time. And then you get a table with it that shows you how the mass decreases with time. And from there, because of the loss of the gas with the time, we will get the rate at which the reaction takes place. We can take the same reaction that takes place inside that beaker and give it to you in another form. So in this case, we have magnesium inside a conical flask. We added dilute acid to it, and the hydrogen gas that is collected via a delivery tube over water in a burette. And in this case, we read the volume of the gas that was formed off, and we plot it versus time. So if we go back, then we see that this is the same reaction, but it's a different way of doing it, a different way of collecting the gas, and also a different way of giving you the data that we received from that experiment. So it's once again important to know that this specific experiment and the previous one are equivalent, and therefore most of your principles will be the same. The next one will again be, this is copper turnings. It could have been magnesium as well, and in this case we added nitric acid. So here the gas that is formed goes through the tube and pushes back the syringe, the piston of a syringe, and then we read off the volume of the gas formed as the gas volume increases with time. So these are all different methods of collecting the information from our practical investigations, and it is very good to familiarize yourself with it. Please ask your teacher to help you with it if possible, for you to be able to do it yourself, or for your teacher to demonstrate it. And the final, not the ideal, but the final option would be to go on the internet and watch videos of how it is done in a laboratory. Now we go to the graphs that's important for reaction rates. This is a graph that should be familiar to you from grade 11. And this is the chemical potential energy curve. And it's very important, we have to label it properly. Our vertical axis gives us our chemical potential energy. Our horizontal axis gives us a reaction coordinate. It can also say time, but many times we use the terms reaction coordinate. The first time where we see energy of the reactants, we see how when the reactants get together, the energy increases drastically and they form an activated complex. We're looking at the black curve in this case. And then at the activated complex, the products are formed and energy decreases again to where the products are formed. And as we know, we say that the difference in energy between the products and the reactants is called delta H, which is the heat of reaction. If you look at the vertical words, it says activation energy without a catalyst. And next to it, for the red curve, we find activation energy with a catalyst. And what we know is the role of the catalyst is to give the reaction a different energy path. It uses less energy to reach an activated complex, and therefore the rate of the reaction is increased by the catalyst. The next type of curve is the Maxwell-Botzmann curve, and we're going to spend a bit more time with this. And first of all, I just want to explain how it differs from the previous one. Previous one, we had chemical potential energy on the vertical axis. In this case, we have a fraction of particles with a given kinetic energy on the vertical axis. So this is not an energy, this is an indication of how many particles in the reaction has a certain energy. our horizontal axis has got kinetic energy of the particles. So the energy in this case is the horizontal axis and not vertical. If you look at the curve, and we're going to stand still there, we find that there's a dotted line to the right, just left of the red zone, that indicates the minimum energy required for a reaction. And what we see in this specific case is that if I go over to the number of particles, the number of particles that has enough energy for a reaction is very low. And therefore, and we see that the bulk of this curve is to the left of that dotted line. So the energy is relatively low, and therefore the rate of the reaction will be slow. As soon as through collision the particles have enough energy, we find that we get into the red zone where it makes effective collisions, and therefore the reaction can take place. So now we're going to look at more detail, and now we change conditions. So what we're going to do now is look at Maxwell-Botzmann curve again, and here I just put in the labels that says that a small fraction of particles will be involved in effective collision, and therefore the reaction rate will be slow. The larger fraction of or percentage of particles will be not be involved in effective collisions, and this is the standard curve. If we now increase the temperature, and there I just want to stand still and talk about what the effect of temperature is. We say that temperature is an indication of the average kinetic energy of the particles. And that means if I increase my temperature, I also increase the kinetic energy of my particles, then they move with a higher velocity or speed, and they have more collisions amongst themselves and more collisions with the sides of the vessel that they're in, and therefore they will have more effective collisions to actually let the reaction take place. So when I increase my temperature, I increase my average kinetic energy of my particles, and when I decrease my temperature, then I decrease the average kinetic energy of my particles. So back to our slides. So now I increase my temperature, and I see that is what happens. And if you see the green curve at this stage, then you will see that the fraction of particles with a lower energy has decreased dramatically. You can see the top of the black curve was a high fraction, top of the green curve is a low fraction. When we go to the right of the dotted line, the line that indicates the minimum energy, we find that the curve is now lifted, and therefore we have more particles that can collide effectively, and therefore the reaction will take place faster. And what happens here is, and I haven't indicated on there, many learners get confused because this graph is higher than the black one, is higher than the green one. They get confused and they think that the temperature for the black curve is higher than the temperature for the green curve. But that's why it's important to note the label on the vertical axis. This is a higher fraction of particles with a low energy, so this is the lower temperature represented by the black curve, and this is a lower number of particles with a low energy, or alternatively it's a higher number of particles with high energy. So the green curve, although it is lower than the black curve, represents the higher temperature. And this is then how we use the Maxwell-Botzmann curve to show that an increase in temperature leads to an increase in reaction rate. We're now going over to another scenario with Maxwell-Botzmann. Okay, there we just add that, lower fraction, and there we've got more particles with effective collisions. And now we go to another scenario where we use a catalyst. So once again, this is our first Maxwell-Botzmann curve, which is standard. If I now add a catalyst, the same thing happens that happens with the chemical potential energy curve. The catalyst causes the minimum energy required to be lower than before. And because this dotted line is now shifted to the left, so that the kinetic energy needed for this collision to take place, for effective collisions to take place, it means more of my particles, everything under this curve, which has got the green lines and the red zone in it. Everything there, that is the fraction. And if we go over, we move it to the vertical axis and we see there's a higher portion or higher fraction of particles that can have effective collisions. And that is how we use the Maxwell-Botzmann curve to indicate the effect of a catalyst on the rate of a reaction.